Okay, picture a ruler in your head. If you measure a piece of string and it lines up right on the 8 centimeter mark, you'd probably say it's exactly 8 centimeters, right? Well, put on your detective hats, because today we're uncovering a mathematical secret that's literally hiding in plain sight. We navigate our days just kind of assuming the numbers we use to measure distance or weight or time are absolute truths. But what if I told you that almost every single measurement you've ever taken is actually hiding a hidden range of uncertainty?
Welcome to This Explainer. Today, we're going to undergo a complete paradigm shift by looking at the principles of approximation and mathematical bounds. You know, we often think of mathematics as this pursuit of perfect, pristine numbers, but the truth is actually way more fascinating. In the physical, messy real world, mathematics isn't just about perfect numbers. It's actually the ultimate tool that helps us manage and calculate the inherent inexactness of reality.
Okay, let's dive into this. Here is our roadmap for today. First, the illusion of exactness. Second, measuring our mistakes. Third, the half-unit rule. Fourth, when errors multiply. Fifth, the division trap. And finally, avoiding common mistakes.
Let's jump into Section 1, the illusion of exactness, shattering the paradigm of perfect measurements.
Before we crunch any numbers, we really need to define what an approximation actually is. Put simply, it's a value that's close to the actual value, but it's not exact. Think about something familiar, like pi. We constantly use 3.14 in our calculations, right? It's incredibly useful, it gets us very close to the truth, but it's still an approximation. It is not the absolute, infinite true value of pi. And honestly, whenever we measure anything in real life, we're doing the exact same thing. To really grasp this illusion, we have to contrast exact values with rounded ones. An exact value is the true value, without a single bit of rounding. This usually applies to things we can physically pick up and count. Like, if you have exactly 12 pencils on your desk, you just have 12 pencils. You don't have 12-point-something pencils. But a rounded value is continuous. It's written to a certain degree of accuracy. Say a machine weighs a package at 7.846 kilograms. We might round that to 7.85, just to make things easier. The measurement looks super precise, but at its core, it's fundamentally a rounded approximation.
Moving right along to Section 2, measuring your mistakes, calculating the gap between approximate and actual. Now that we know our measurements are pretty much all approximations, how do we systematically quantify those little inaccuracies? Like, how do we measure the gap between what we jotted down and reality? Well, it's a simple bit of math called absolute error. It is simply the positive difference between the actual value and your approximate value. So, say an actual value is 51.6 centimeters, but we roughly recorded it as 52 centimeters, we just subtract them and take the absolute difference. The absolute error here is exactly 0.4 centimeters. We were off by a flat 0.4.
But hold on, absolute error doesn't tell the whole story, does it? Because think about it, being off by 2 centimeters matters a whole lot if you're measuring a 5-centimeter bug, but it doesn't matter much at all if you're measuring a giant football field. And that's exactly where percentage error comes in. If a value is measured as 80, but the actual real-world value is 78, our absolute error is 2. To find the percentage error, we divide that error of 2 by the actual value of 78 and multiply by 100. That gives us a 2.56% error. This brilliantly shows how a relatively small absolute mistake scales proportionally against the true measurement.
All right, Section 3, the half-unit rule, the golden rule of mathematical bounds.
This brings us to a really cool concept, predicting the hidden range of a measurement. You've absolutely got to commit this golden rule to memory. When a number is rounded, the maximum possible error is half of the rounding unit. Because we round things, every single measurement we take has a strict lower bound, like the absolute smallest it could possibly be, and an upper bound, the absolute largest it could be. And the whole shebang is dictated by this half-unit rule.
Let's actually see this law in action. So take a given value of 6 centimeters, round it to the nearest whole centimeter. The rounding unit is 1, right? Well, half of 1 is 0.5. So your lower bound is 5.5, and your upper bound is 6.5. What about 4.7 meters rounded to the nearest 0.1 meter? Half of 0.1 is 0.05, so the true value is completely trapped between 4.65 and 4.75. Or, let's say 250 kilograms, rounded to the nearest 10 kilograms. Half of 10 is 5, so the hidden boundaries are 245 to 255. See how the specific rounding unit directly dictates the exact boundaries?
Let's just quickly pace ourselves through the methodical 4-step process to uncover these boundaries for literally any measurement you'll ever encounter. Step 1, identify what the value has been rounded to. Step 2, find half of that rounding unit. Step 3, subtract that half unit to get your minimum, your lower bound, and Step 4, add that half unit to get your maximum, your upper bound. It is a wonderfully systematic, foolproof process.
Let's see how this builds in Section 4. When errors multiply. Calculating bounds in addition, subtraction, and products.
So, what happens when we take these inexact, rounded numbers and plug them into real-life mathematical formulas? Well, first, let's explicitly contrast addition and subtraction. Addition is highly intuitive. If you want the absolute minimum total of two measurements, you just add their lower bounds together. Easy. But subtraction is a tricky beast. To find the absolute minimum difference between two values, you have to take the smallest possible starting number, the lower bound of x, and actually subtract the absolutely largest possible number from it, the upper bound of y. Let's look at calculating the area of a simple rectangle. Imagine one that's 12 centimeters by 5 centimeters, both measured to the nearest centimeter. You'd normally just say, 12 times 5 is 60. The area is 60. Actually, scratch that. It's not that simple. When we multiply the lower bounds, 11.5 times 4.5, we get a minimum area of 51.75. And when we multiply the upper bounds, 12.5 times 5.5, we get an upper bound of 68.75. That is a massive gap. The real area could be anywhere from almost 52 all the way up to nearly 69 square centimeters. This really shows how multiplying errors significantly widens the possible range of our final answer.
Now for the big one. Section 5, the division trap. Why dividing by smaller numbers creates larger bounds.
We've reached the climax of these mathematical concepts. If you thought multiplication widened the gap, just wait until you see division. So the absolutely crucial point here is this inverse relationship. When you're calculating bounds involving division, to get the absolutely smallest possible answer, you have to take your smallest numerator and divide it by your largest denominator. And conversely, to get the absolute maximum possible value, you must divide your largest numerator by your smallest denominator. It's this weird cross-pairing of bounds. Because dividing by a larger number gives a smaller answer, you really must grasp this inverse relationship to avoid falling into the trap.
Let's anchor this abstract math to a real-world scenario. Imagine you're tracking a car's speed. We know speed equals distance divided by time. Say the car travels 120 kilometers, measured to the nearest 10, in 4 hours, measured to the nearest hour. To find the guaranteed minimum speed, our lower bound, we take the lower bound of the distance, which is 115 kilometers, and we divide it by the upper bound of the time, 4.5 hours. 115 divided by 4.5 gives us roughly 25.56 kilometers per hour. And there it is. That is the division trap in action.
Almost there. Section 6, avoiding common mistakes. Mastering the pitfalls of approximation.
To empower you to confidently conquer these calculations, whether you're taking an exam or just doing some DIY around the house, let's do a rapid-fire review of the 3 biggest traps people fall into. First, forgetting to have the unit. If you're rounding to the nearest 10, your error is 5, not 10. Second, falling into the division trap we just covered and using the wrong bounds. Third, and this one is absolutely crucial, including the upper bound in your inequality notation. Notice how we use strictly less than for the upper bound, not less than or equal to. Why? Because if a measurement rounded to the nearest unit actually hit that upper boundary exactly, say 8.5, it would automatically round up to the next number, 9. So the true value has to always be strictly less than the upper bound.
And this brilliantly illustrates what is actually tested if you're studying this formally. Here is your definitive checklist for total mastery. You need to be able to find the lower and upper bounds of a basic measurement. You'll need to find the max or min values of expressions, especially tracking how those errors compound in area, volume, speed, or density. And finally, you must be comfortable determining absolute and percentage errors from those rounded values.
So as we wrap up this explainer, I really want to leave you looking at the numbers around you just a little bit differently. We've seen how a tiny rounding unit creates bounds, and how those bounds multiply and divide to create huge ranges of uncertainty. So it kind of begs the question, if practically all of our measurements are just approximations, how much of our engineered, constructed world is truly built on the illusion of exactness? Keep questioning the numbers, and thank you so much for learning with us today.